All right, so the last topic that we're going to talk about today is file I/O in C. So this is the last major thing that you need for the first couple projects. So the C standard library provides some file stream handle definitions. It's called file in all caps, and they're basically structs that you refer to with a pointer. They're a little different from the other structs that we'll use this semester because they are what are called opaque. And what this means is that while the standard specifies that they should exist, it doesn't specify what the internal representation should be. And this allows us to interact with files in a portable manner where the actual details of interacting with the system could be different depending on which computer system we're working on. And we'll learn more about file systems later on this semester. So file star is what you would use to refer to a file stream. And there are various functions that the C standard library provides for interacting with these files. So you can open a file, you can read a character, you can read a line of text, you could read some binary data, you can set your current position in the file, you can write formatted data, you can write binary data, and then finally you need to remember to close the file when you're done with it. So these are all documented on the function reference website, which I'll include a link to on this below this video. So you should take some time getting familiar with these, but you'll also be using them in the next couple projects, so you'll get a chance to become familiar with them there as well. Just like Java, there are a few standard file streams. So there's a standard input, standard output, and standard error. These are just like system.in, system.out, and system.error in Java. These are all available to all programs by default. You don't need to open or close them. They are flushed when you send a new line to them. And if you are using, these are generally meant to be interacted with on the command line, so you can type data and it'll come in through standard in, or if you print data out to standard out, it'll go to the screen. And so generally when using these, we use the formatted input and output, at least when we're interacting with text. And so the way that these work is that they are variable argument functions. We've sort of seen them a little bit already. Basically, you send as its first parameter a format specifier string. And this is just a string that has any hard-coded text data that you want to print, and then little format specifiers wherever you want to insert data from variables. So for instance, %d for a signed integer, or %c for a character, or %s for another string. And so for each of those type specifiers that you put into the format string, you would then include another argument after the format string that actually has the variable or the expression that you want to be inserted into the string at that place. So this is an example of a function that takes a variable number of arguments, which is possible in C. And it's done using a mechanism called var_args that we're not going to study this semester, but it is kind of interesting if you're interested in looking into it further. So here's a question to think about for a second. What is wrong with the following code? So we declare a buffer and then we use fgetS to read into it. So maybe at this point, pause the video and take a look at this and see if you can figure out which of these answers is correct. So A, B, C, or D if there is a problem with this code, or E if there is no problem with this code. Okay, so I probably wouldn't be talking about this in a lecture, right, if there wasn't anything wrong with it. So E is probably a pretty easy answer to eliminate. If you look at the reference for fgetS, you'd see that it has the right number of parameters, so that's fine. So it must be A, B, or C. You might be tempted to think that the problem is that the buffer is not initialized before calling fgetS, and that's true. The buffer is not being initialized, but it turns out that that's not really the problem here, because the fgetS call itself is going to be reading data into the buffer. So in a sense, we are initializing that buffer with the call to fgetS. So that by itself is not the problem. B may be a little tempting. So the buffer is the wrong size, but that's not really the problem because we don't really know, looking at this code, how big the buffer needs to be. The programmer has declared it to be 20 characters long. So that's 19 if you 19 real characters plus a null terminator. So, is that the right size? We don't really know without further context. So we'll assume that that's correct. So that means that by process of elimination, the answer is C, which also you probably could have identified straight away just by observing that the maximum character, so if you looked at the definition for fgetS, you'd see that this is the maximum length that we can print into the buffer, or that we can read into the buffer. This number is greater than the actual size that we have allocated for the buffer. And as we've seen before, C is going to allow you to do that, and it will just keep saving data right off the end of the buffer. And so you'd have what's called a buffer overrun or an out of bounds access. And this is a major source of both bugs and security issues, as I mentioned before. And this has been a recurring problem for decades now. And so this is sort of similar to the copying strings problem that we saw a little bit earlier. And this is a common source, like I said, of security vulnerabilities. So the best practice here is to declare a fixed size buffer, use the safe input functions, make sure that all of the sizes match. It's useful to use constants here so that if you want to change the size later, you don't have to go changing the size all over the place. And in order to sort of instill good habits here at the very beginning, we are going to just say that in 261, you're not allowed to use functions that the community has generally decided are unsafe. So for example, getS, which by itself doesn't do any sort of bounds checking. And so that is considered to be an unsafe function, and you should not use it in 261. You will lose points on the programming assignments if you use an unsafe function. So here is a partial list of unsafe functions. So A2I, which converts a string to an integer, and so forth. And over here, we have the safer alternatives. So for instance, if you want to use A2I to convert a string to an integer, here's a safer alternative, str to L. There's a longer list of these in the function reference, which again is going to be a link underneath this video. So make sure you take some time to look at that list and make sure that you don't use any of the unsafe functions. This is particularly important, and this comes up a lot when students try to use code that they found on the internet. I'm generally not opposed to you going out and finding solutions on the internet for things that are amenable to that. You should always make sure that you cite your sources if you decide to use code that you found online in a project to avoid an honor code violation. But I would also caution you against doing that because of things like this, where the authors of that code that you find online may not be as careful as we need to be in this course. And so that some of these unsafe functions may sneak in via code that you found somewhere else. And this is just a good principle in general, which is that you really should be careful with code that you find online. You should never, ever use code that you don't fully understand or that you haven't personally verified to be safe.